You've seen this 1,000 times. You're boarding a plane, walking across the tarmac, and you glance at the engine. Right there, on the spinning nose cone, there's a spiral pattern. Red and white, sometimes yellow and black, always rotating. Most people assume it's decorative. Maybe it's branding. Maybe it's just to make the engine look less industrial. But that assumption is completely wrong. That spiral isn't decoration. It's a critical safety system. And without it, ground crew deaths would be far more common than they are today. So here's the real question. Why does a multi-million-dollar jet engine need a painted spiral to keep people alive? The answer involves human perception, optical illusion, and one of the most dangerous zones around any aircraft. Let's break it down. First, we need to understand the problem. A jet engine doesn't just sit there. Even at idle thrust on the ground, the fan at the front of a modern turbofan engine is spinning at around 1,000 to 3,000 revolutions per minute. That's 16 to 50 revolutions per second. At those speeds, the blades become invisible to the human eye. You can't see motion. You can't see rotation. What you see is a smooth, blurred disk. And that's where the danger begins. Imagine you're a ground technician. You're doing a pre-flight check. The engines are running at idle. You need to inspect something near the inlet. You look at the engine. It looks still. There's no obvious visual cue that anything is moving. Your brain doesn't register threat. You step closer. And in that moment, if you get too close, you get pulled into a zone of violently rotating titanium blades moving faster than your reaction time. The outcome is catastrophic. This isn't hypothetical. It has happened multiple times. And it's why the spiral exists. The spiral creates what's called the stroboscopic effect. When the cone rotates, the contrasting pattern generates a flickering visual signal. Your brain interprets that flicker as motion. It's not about seeing the blades. It's about seeing that something is rotating even when your eyes can't track individual revolutions. The spiral doesn't stop at a safe speed. It's designed to remain visually apparent across the entire range of engine operation, from idle to takeoff thrust. That means the pattern has to work at 1,000 revolutions per minute and at 5,000 revolutions per minute. And it does. Let's talk about the science behind it. Human vision operates on persistence of vision. When something moves faster than about 10 to 12 frames per second, your brain blends the images together into continuous motion. But if something spins much faster than that, you lose the ability to perceive it as motion at all. It just becomes a static blur. The spiral disrupts that blur. The high contrast edges of the spiral create periodic changes in light intensity as they pass a fixed point in your visual field. Your peripheral vision is especially sensitive to this kind of flicker. Even if you're not looking directly at the engine, your brain detects the motion signal and triggers a warning response. You instinctively know something is spinning. You don't approach. Now, here's the engineering detail most people miss. The spiral isn't random. It's carefully designed. On most modern turbofan engines, the nose cone, also called the spinner, rotates with the low-pressure fan assembly. The pattern is typically a two-tone or three-tone spiral, starting from the center and radiating outward. The spacing, width, and color contrast are not arbitrary. They're optimized for maximum visibility under varying lighting conditions, from bright daylight to dim hangar lighting. Red and white is common because red has high visibility and white provides maximum contrast. Some engines use yellow and black for even greater contrast, similar to hazard markings. But there's more to this system than just visibility. The spiral also serves a secondary diagnostic function. Maintenance crews use it to visually verify that the fan is rotating smoothly. If the engine is running but the spiral appears stationary or stuttering in an unusual way, that's an immediate indicator of a problem. It could mean the fan isn't turning at the expected speed. It could indicate a mechanical fault. The spiral becomes a real-time visual tachometer, a simple analog tool in an otherwise highly digital system. Let's talk about where this design came from. The use of spirals on rotating aircraft components isn't new. Propeller-driven aircraft have used similar patterns since the early days of aviation. Spinning propellers at rest look stationary. Add a spiral or a stripe, and suddenly the motion becomes obvious. When jet engines became widespread in the 1950s and 60s, the same logic was applied. But the problem was more severe with jets. Propellers are large and extend beyond the fuselage. Jet engine inlets are recessed, often at waist or chest height, and the fan blades sit inside a cowling. The danger zone is less obvious. The spiral became not just useful, but essential. There's also a regulatory aspect. Aviation authorities like the FAA and ESA don't mandate the exact design of the spiral, but they do require clear visual indicators on engines to prevent ground crew accidents. The spiral has become the industry standard solution. It's simple, passive, requires no power, no electronics, no maintenance beyond occasional repainting, and it works. In engineering, that's called an elegant solution. Now, what happens if the spiral isn't there? Some smaller turbofan engines or older designs don't have spirals. In those cases, alternative methods are used. Warning lights, audible alarms, physical barriers, painted safety zones on the ground. But none of them are as immediately intuitive as a rotating visual pattern. The spiral communicates danger in a universal language. No training required. No language barrier. You see it spinning, you know to stay back. Here's an edge case. What about when the engine isn't running? The spiral is still there, but it's static. Does that create confusion? No, because when the engine is off, there's no noise, no exhaust heat, no visible airflow distortion. The absence of those cues, combined with a stationary spiral, signals that the engine is safe to approach. But the moment you hear the engine spool up, even before it reaches idle RPM, that spiral starts moving, and your brain registers it immediately. The system works across all operational states. There's also a human factors consideration. Ground crew work in high-noise, high-stress environments. They're managing multiple tasks, often under time pressure. Cognitive load is high. In that context, passive safety systems that don't require active attention are critical. The spiral doesn't require you to remember a rule or check an indicator. It's always there, always visible, always communicating. That redundancy saves lives. So, the next time you walk past a jet engine and see that spiral, understand what you're looking at. It's not art. It's not branding. It's a carefully engineered optical warning system designed to exploit the way your brain processes motion and flicker. It exists because rotating machinery at 3,000 revolutions per minute is invisible to the naked eye, and invisible threats kill people. The spiral makes the invisible visible, and that's why it's there. To me, that's the beauty of engineering. The best solutions are often the simplest. No sensors, no computers, just paint, geometry, and an understanding of human perception. And it works every single time. Now, if you've ever wondered why jet engines are mounted under the wings instead of on the fuselage, I've covered that in another video. But let's go deeper into the mechanics of why this specific visual pattern is so effective. The human eye contains two types of photoreceptor cells, rods and cones. Cones handle color and detail in bright light. Rods handle motion detection and peripheral vision in low light. When you're near an aircraft, especially in outdoor conditions, both systems are active. The spiral works because it triggers both. The high contrast between the spiral's colors activates your cones, making the pattern stand out. The motion of the spiral activates your rods, particularly in your peripheral vision, which is extremely sensitive to movement. This dual activation creates a strong, instinctive response. Your brain doesn't just notice the spiral. It prioritizes it as a potential threat. Now, consider the aerodynamic environment around a running jet engine. There's a massive volume of air being drawn into the inlet. At takeoff thrust, a large turbofan engine can ingest over 1,200 kilograms of air per second. That creates a powerful suction effect extending several meters in front of the engine. Loose objects, tool bags, even people have been pulled into engine inlets. The spiral warns you not just of the rotating blades, but of the entire danger zone. It's a visual marker for an invisible aerodynamic hazard. There's also a psychological component. The spiral creates a sense of unease. It's not a natural pattern. It doesn't exist in nature. When you see it spinning, your brain recognizes it as artificial, mechanical, and therefore potentially dangerous. That instinctive wariness keeps you alert. Compare that to an unmarked, smoothly spinning disc. Your brain might interpret that as non-threatening or even ignore it entirely. The spiral doesn't allow that. It demands attention. Let's examine a real-world case. In 2006, a ground crew member at El Paso International Airport was fatally injured after being pulled into the intake of a Boeing 737 engine. Investigations revealed that the person had approached the engine while it was running at idle, likely unaware that it was operational. Incidents like this, although rare, reinforce why the spiral is critical. It's a last line of defense when other safety protocols fail. If someone is distracted, fatigued, or simply makes an error in judgment, the spiral provides an immediate, passive warning. Modern engines have additional safety features. Inlet warning lights, ground crew training, clearly marked safe zones. But the spiral remains the most universally effective. It doesn't rely on batteries. It doesn't fail if someone forgets to turn it on. It's always there, doing its job, as long as the engine is rotating. That reliability is why it's still standard across nearly every commercial turbofan engine in service today. Another interesting detail: the direction of the spiral matters. Most spirals are designed to appear to rotate in a specific direction depending on the rotation of the fan. On most turbofan engines, the fan rotates clockwise when viewed from the front. The spiral is painted to enhance that visual rotation. If the spiral were painted in the opposite direction, it could create visual confusion or reduce effectiveness. Engineers test these patterns extensively to ensure they work as intended across different lighting conditions, viewing angles, and rotation speeds. There's also the question of maintenance. Over time, paint wears. The spiral can fade, chip, or become obscured by dirt, oil, or exhaust residue. That's why spirals are inspected and repainted regularly as part of routine engine maintenance. A faded spiral is less effective. A missing spiral is a safety risk. Airlines take this seriously, not just because of regulatory requirements, but because the cost of repainting a spiral is negligible compared to the cost of an accident. So, when you see that spiral, you're looking at over 70 years of iterative safety design. It started with propellers. It evolved with turbojets. It perfected with turbofans. And it will continue on future engine designs because the fundamental problem hasn't changed. Humans can't see fast rotation, but they can see patterns that disrupt their perception. And that disruption saves lives.